All right, so I'm going to introduce improper integrals here, and one of the things we're going to use when we deal in improper integrals is limits. Okay, so I want to reintroduce something to you or review for you L'Hopital's rule, which is solving indeterminate limits. So that is limits of the form 0 over 0 or infinity over infinity, right? Something that we can't define. Okay, so if we have a limit as x goes to u of f of x over g of x, and that ends up in a indeterminate form such as infinity over infinity, okay, we can't define that limit. We can take that limit as x goes to u and take the derivative of f of x and divide it by the derivative of g of x and get what the value of the limit is. Okay, and assuming that we don't end up in another indeterminate form, in which case we'd iteratively go until we have a value. Okay, so let's do a quick example of this and then we'll move on to our improper integrals. Right, so if we have the limit of x squared minus 9 is equal to x squared minus x minus 6. Okay, well, remember from last semester, we could rewrite this as the limit as x goes to 3, and we could factor it out. X plus 3, x minus 3, okay, over x plus 3, x minus 2, or x minus 2x plus 3. Right? X minus 2, x plus 3. Right? We can factor that to x minus 3, x plus 2. Right? There we go. All right, brain and mouth get together. And those are 3's, not 5's. I will rewrite those for you. X plus 3, x minus 3. Right? So that's just factoring the numerator and the denominator. Right? And then we'd get a cancellation here, and we'd end up with a limit of x plus 3 over x plus 2, right? Which we could then do the direct substitution, right? And we'd end up with 6 over 5. Right? So then we'd say the limit of x goes to 3 of x squared minus 9 over x squared minus x minus 6 is 6/5. Remember, this gave us a problem in the beginning because if we plug in 3, we get 0 over 0, and that is not defined. Right, so if we apply L'Hopital's rule, we can say the limit as x goes to 3. Now we take the derivative of x squared minus 9, 2x, and we take the derivative of x squared minus x minus 6, which is 2x minus 1. And now we can substitute those directly to get 6/5. Okay, so if we're gonna evaluate these improper integrals, and there may be cases where we need to use L'Hopital's rule, and we're gonna evaluate these improper integrals, and there's gonna be cases where we take the limits and we get right to where we're supposed to be. All right, so let's look at what is an improper integral. Well, there are a handful of things that make improper integrals. All right, we'll go over those sort of in more detail in a minute. But in general, it's when we have limits of a definite integral and infinity is involved. So to infinity to negative infinity, right, or to negative infinity to infinity. Right? So somewhere infinity in the limits. If we take the integral of something and the limit equal, or we take the integral and the integral goes to infinity, okay, or if we take the integral of something and there's a discontinuity in it and we have to treat it specially. Okay, so here we've got x over 16 minus 2x squared. Well, a negative square root of 2, okay, there's a vertical asymptote in there because it's not defined, right? We do have x over 0, so we can't have an integral. So we have some sort of vertical asymptote that we have to deal with, okay? All right. So if we start with how are we going to deal with these improper integrals? So if we start with the integral of infinity, 1 to infinity of e to the 4x dx. Okay. All right. Well, we're going to start by saying, well, let's take the limit as t goes to our problem value, right, which here is infinity, of e, all right, to the integral of 1 to t 4x dx. Okay, so we're substituting t in the limit, the upper limit or the lower limit, right, of our integral. Meaning, if we need to substitute our upper and lower limits, we're going to have to evaluate them separately. Okay, so keep that in mind. For this case, we only have infinity in one spot, so we can take care of it in one spot. So we have the limit as t goes to infinity of 1 to t 4x dx. Okay, well, what does that mean? Well, now we can evaluate our integrand. Right, so the limit as t goes to infinity of 1 over 4x, or 1 over 4 e to the 4x. And we're going to evaluate that from 1 to t. Now t is not going to 8, t is going to infinity. Okay. Okay. So that's where that one stands, right? So now we can evaluate the limit. All right. Well, how do we evaluate the limit? We have to also do the evaluation theorem. So this is going to become the limit as t goes to infinity of 1/4 e to the 4t minus the limit as t goes to infinity of 1/4 e to the 4 times 1. Okay, well, e to the 4 times 1, that's just going to be the constant, right? There's no t to make a substitution for. If I go on the left, what I'm going to be doing is I'm going to go e to the 4t, right? So now I evaluate the limit. I get that the limit goes in 1/4 e to the 4 to infinity. Well, e to infinity is just infinity, so I'm going to get infinity minus 1/4 e to the 4th, which is infinity minus a constant, or just infinity. So we would say the integral of 1 to infinity of e to the 4x dx is equal to infinite, right? So the value is an infinite. Okay, so that's an improper integral now for two reasons. A, infinity is in the limit, and infinity is the result. Okay. All right. All right. So we'll go through one more example. Okay. So then we have the integral of 0 to -4. Okay. 0 to -4 of x over 16 minus x squared. X squared dx. Now we said we're going to have to break this up into two integrals, right? 0 to the -2 square root 2 x over 16 minus 2x squared plus the integral from -2 square root 2 to -4 x over 16 minus 2x squared dx. All right, I have to make the sum of each of those integrals. So now how are we going to do this? Well, we're going to take the limit of each one, right? Now our problem here is still -2 to the square root 2. That bottom goes to 0. Okay, so there's still an issue there, okay, as far as the function is concerned. So we're going to take the limit as t goes to -2 square root of 2, right, of the integral from 0 to t x over 16 minus 2x squared plus the limit as t goes to -2 square root of 2 of the integral of t. Oops, sorry. Whoa, all over the place. Let's get that back. Okay. As x goes to t to -4, right, of x over 16 minus 2x squared dx. Well, now, so here we're dealing with the same integrand, so we only need to find one. We only need to get an antiderivative once. Okay, so I'm going to be taking the limit as t goes to -2 square root 2. Now, to evaluate x minus 16 over 2x, I need the antiderivative. Now, that's independent of whether it's improper or not. Right? The antiderivatives don't change. It's just in how we evaluate them. Okay? So here we're going to do u substitution, where u is the entire denominator. Okay, 2x squared minus 16, or 16 minus 2x squared. All right, giving me that dx. All right, the derivative of that is -4x. All right, so when I bring in du, it means my antiderivative is going to be -1/4 1 over u. Okay, all right, and then this is now still going to t, right? Du, right, from 0 to t. So my limits are now still in terms of t. Okay, and now I have 1/4 du, right, and I have the same thing over here. The limit Right, as t goes to negative 2, square root 2, the integral from t to negative 4 of negative 1/4 1 over u du. Alright, so let's take that one step further. Okay. 1 over u is the natural log of u, okay, and u was 16 minus 2x. So now we're taking the limit as t goes to negative 2 square root 2. Now we're not taking the integral, right? We're going to have negative 1/4 times the natural log of the absolute value, 16 minus 2x squared. Okay. Evaluated from 0 to t, plus the limit as t goes to negative 2 square root 2, from t to 0. Oops. All right, doing the same thing over here, minus 1/4. Natural log of 16 minus 2x squared, okay, from 0 to t. All right, so we have those two limits to evaluate. Right, so we can do direct substitution into them both. Right, so I have minus 1/4 times the natural log of 16 minus 2t squared. Okay, absolute value now, 16 minus 2t squared. And this is going to be plus 1/4 natural log, absolute value, 16 minus 2 times 0 squared. Okay. All right, and then we'd have the other side over there. Okay, and we have to do some quick math, right, or substitutions, right? 16 minus 2t. Right, we're still taking the limit of this whole bit. Oops, forgot to write the limit out front. When you're doing these, let's never forget we're taking the limit as t goes to some value, negative 2 square root 2. Okay, so now we can plug negative 2 square root 2 in. All right, to the anywhere we see t, we'll have negative 1/4 times the natural log of 16 minus 2 times negative 2 square root of 2 squared, absolute value, plus 1/4 natural log, absolute value of 16. Okay. So we can do that out pretty quickly, right? Asking ourselves what the natural log of 16 minus 2 times negative 2 times the square root of 2 squared. All right, so this first value, right, we're going to have negative infinity, 1/4 plus the natural log of 2. Okay, so negative infinity plus the natural log of 2. Okay. And we're going to go to the other side. All right, and we evaluate our limits. All right, we're going to do the same thing. We're going to have the same integrand. We're going to go, all right, except now these limits are t to negative 4. Right? T to negative 4, so negative 4 squared is 16 times 2, 16 minus 32, and 0.4, oops, 1/4 times the natural log, all right, of 16. Just still going to be natural log of 2. Okay. All right, 16, we're going to go 4 squared. 16 times 2 is 32. 16 minus 32. It's going to be negative 16. All right, we're going to take the absolute value of that, whatever. Okay, now this is going to be negative, right, because we're at negative 1/4. Okay, so negative natural log. And then from that, we're going to now subtract or add, right, the value of 1/4 natural log 16 minus t squared. Right, the value over there. So essentially, we're going to end up with adding infinity.